Hello guys, welcome on Tesla Adventures. In this video today we are going to discuss the biasing of PN junction diode. Now biasing means the way to connect the battery, and this is the symbol of PN junction diode, and this side is represented by P side. In fact, this is P side and this is N side. So this is the symbol of PN junction diode. So first of all, let us discuss about the forward biasing. So in forward biasing, we will be connecting the P side of the diode to the positive terminal of the battery and the N side of the diode to the negative terminal of the battery. This type of biasing, in which P is connected to the positive and N is connected to the negative terminal, is called as forward biasing. And in forward biasing, obviously you can see that the external electric field is from P side to N side, like that. And we know that barrier electric field is from N side to P side. So in forward biasing, the external electric field is opposing the barrier electric field. And in the video in which we have studied about the formation or the junction theory of the diode, we have already discussed about the fact that the barrier electric field opposes the diffusion current and supports the drift current. Now, if the external electric field is opposing the barrier electric field, then we can say that external electric field is supporting the diffusion current and opposing the drift current. And we know that diffusion current is due to the majority charge carriers. So you can say that this external electric field pushes these electrons, these holes, towards the junction, and these electrons towards the junction. So a current flows, which is the diffusion current, which is due to the majority charge carriers through the diode. And this current, these holes and electrons recombine on the junction. And due to their recombination, photons are emitted from the junction, like that. Okay, so first of all, this in forward biasing, the external electric field opposes the barrier electric field, and external voltage also opposes the barrier voltage. So we can say that the net voltage in the depletion region decreases, and the net electric field in the depletion region decreases. So width of the depletion region decreases because majority charge carriers are pushed towards the junction, so this width decreases. The current flowing in this diode in forward biasing is of order of milliampere, and it is very important to note that what is happening here. Here you can see that, let's suppose there are 100 holes here and there are 100 electrons here. So what will happen after recombination of these 100 holes and electrons? More holes will be generated at this point. You can see that this battery positive terminal is pulling the conduction electrons like that, and those conduction electrons are generated by the jumping of electrons from valence band to conduction band. So we can say that at this end, the conduction electrons the valence electrons are being pulled by this positive terminal of the battery, and when they are pulled, then holes are generated, and those holes are moving in the forward direction, and the electrons taken by this battery from this diode are given to the negative side of the N side of the diode, and these electrons are fulfilled here, and these move forward like that. So this is how the deficiency of holes and deficiency of electrons is fulfilled by the battery. So this is very important to note. Now we can say that if the depletion region width decreases in forward biasing, so we can say that the resistance of diode junction. See, diode offers two types of resistances. First is thermal resistance or Joule's resistance, which we see in normal conductors, that in normal conductors electrons experiences some resistance in moving. So the same resistance is offered by diode also, and the junction of the diode is also offering some resistance to the majority charge carriers, because the electric field, barrier electric field at the junction is offering some resistance to the majority charge carriers. So the diode, the total resistance of the diode is the sum of junction resistance as well as the resistance of diode, which is Joule's resistance of diode. So this is the forward biasing, and this is again the theory which I already explained, and you can take the screenshot of this theory. And it is very important to note that if this diode will allow the current to flow through it only if the external voltage is greater at least from the barrier voltage. So if external voltage is greater from the barrier voltage, then only this diode junction will allow the current to pass through it. Obviously, because if we say that barrier voltage is opposing the flow of majority charge carriers through the junction, and the external voltage is supporting the flow of majority charge carriers through the junction. So to flow the majority for the flow of diffusion current through the junction, or for the flow of majority charge carriers through the junction, it is very important that external voltage is greater at least from the barrier voltage. So diode starts to conduct when the external applied voltage is greater than the barrier voltage. Okay, and if we draw this forward characteristic graph. Now characteristic graph is VI graph, where I is plotted on y-axis and voltage is plotted on x-axis. So this graph is starting like that diode starts to conduct significantly at a voltage which is equal to 0.7 volt for silicon and which is equal to 0.3 volt for germanium. And this is also called as knee voltage. We have already discussed that diode will allow the passage of current only when the external voltage is greater than the barrier voltage. So in a kind, it is, you can say that it is a barrier voltage, and it is known as knee voltage here. Now diode follows this relationship, and there is a very small region in which diode follows the Ohm's law, which is the linear relationship between V and I, but that region is very small. And if we keep on increasing the accelerating voltage, then a time will come then when current will be to a significantly higher amount, so that due to Joule's heating, diode will get burned off. So for example, the maximum current which this silicon diode BY126 can bear is 1 ampere, which means that after this current, the diode will be burned out due to the thermal heat loss, and diode could not be recovered after burning. So this diode will be permanently damaged after flowing the current which is greater than the maximum current. Okay, and if we talk about the resistance of the diode, so that if we say that there are two types of resistance in the diode that it offers. One is the static resistance of the diode. It is the resistance offered by the diode when we are connecting a DC battery source to the diode and the current flowing through the diode is DC. So we can say that the static resistance of the diode is the ratio of DC voltage to the DC current flowing through the diode. And the static resistance of the diode in forward biasing is around 50 ohms. And if we talk about the dynamic resistance, then dynamic resistance is actually the resistance offered by the diode when AC current is flowing through the diode. So it is the ratio of small change in the forward AC voltage to the small change in forward AC current. This is the dynamic resistance. And let me tell you that this dynamic resistance is around 59 ohms to 50 ohms or 90 or 100 ohms. This is the range. And the current flowing through the PN junction diode in any biasing, in either forward or in either reverse biasing, is I is equal to I naught e to the power V upon neta k Te, where I naught is the reverse saturation current, which we would be discussing in the reverse biasing. And V is the accelerating voltage, neta is the emission coefficient, which is 1 for germanium and which is 2 for silicon. K is the Boltzmann constant, and T is the absolute temperature, E is the electronic charge. So I would be discussing this equation in the second part in the reverse biasing in detail, and let us wait for that video. And this was the complete forward biasing, which is associated with the PN junction diode. So let us move on the next video. Thank you.